Hey folks, Todd Coburn here with your Aerospace Structures series. This video is for vector statics for aerospace engineers, and today we're going to focus on rigid bodies. In order to do, now we've been working on particles and how forces how action, reaction, equilibrium, and components work on particles, something that can be treated as a point in space where these forces are acting. Today we're moving into rigid bodies, bodies that are larger. So basically that word rigid, all this means is we're talking about something that is the way the problem is set up. You need something more than a particle for where these forces are acting on it. If the thing is larger and you have a force acting on it, you're going to develop forces and potentially moments on this, and that's going to affect the conditions of equilibrium. And we call this rigid bodies. The reason we use that word rigid, this is not a particle. The reason we use the word rigid is if it actually deflects, that can screw up or modify the way that thing responds to those forces and moments that are being applied. So we'd use that term rigid bodies. We're talking about something that's larger, which means it's large enough that the forces can't all be idealized as if they're acting on a single point. And we're saying it's rigid so they won't have any of the complication that occurs when something is not rigid. In the process, in order to do this in 2 and 3 space, now, a lot of times we're going to actually analyze these with simple scalar operations when we get into industry. But to do anything more complicated, we're going to need to also understand vector products, cross product, dot product. And these are tools of the trade that are needed not only for statics, but for a wide variety of other engineering and orbital mechanics kind of operations. So in this video, I'm going to actually address those, but I'm going to kind of skate over them quickly because I made 2 sub-videos for you. This video is 5, and 5A and 5B go into cross products, dot products, and mixed triple products. So I'm going to encourage you to first watch 5A, then watch 5B. Then you will be armed with the tools that will make it easy for you to apply those tools to rigid bodies as we're going to discuss here. Got that? Okay, so let's get started. Okay, so in the past few lectures, we've treated something that can be idealized where the whole system can be idealized as a particle. Obviously, if we have a little particle and we have a bunch of forces applied, that can be a particle. However, a spacecraft, a rocket, and an aircraft can all be analyzed as particles in certain ideal environments. For example, when we start looking at the detailed forces and moments within an aircraft, we're going to need to go beyond that and look at it as a rigid body and then as a flexible body. But in order to do a lot of the calculate the basic forces on the aircraft and what its acceleration is based on the resultant thrust and lift forces, we often can do a lot of the early analysis treating that aircraft as a particle, just kind of squishing it together and looking at what the net forces are and looking at what the acceleration and directions and velocities are as a resultant of those forces. Later, we need to drill down when we want to understand what's going on in the aircraft. We're going to have to analyze it as a rigid body or as a flexible body. So a lot of this has to do with the judgment of the analyst. Can this be idealized? Is an idealization of treating this like a particle sufficient for the information I'm trying to glean from the problem? Or do I need to try to idealize it with a higher order idealization like as a rigid body? Okay? So that's what this first little bullet is saying. Buren Johnson, Merriam and Craig, Hibbler, these are elementary texts, all of which deal with this quite well. I use a little more of the Buren Johnson content in this video, okay? We're going to need to understand. Now, this is where we find out about moments. We've been learning about forces, and we're going to find out when a force acts through a point, then all we need to do is understand the force, the translational effects of that force. But when that force is applied at some distance from the point, if it's not going through the point, but is applied at some distance, that perpendicular distance causes a moment. You can see this when you're trying to take your tire off your car with a wrench. You get a force, and the further out you put it, the more moment you can apply for the same force. That's what we're going to be dealing with. Moments of forces about points, moments of forces about axes, and moments due to a couple, which is a fancy word that talks about two equal, not romantic forces, but forces that are equal and opposite and separated by some distance. Okay, so as we learned so far, we're always going to be dealing with action-reaction pairs. For every force, there's an equal and opposite reaction. It has an influence which has to be completely reacted. It's going to be transferring through structures, and it's going to be reacted somewhere. That's the idea of equilibrium that we're going to keep on applying throughout our statics journey and onward into structures 1, 2, and dynamics. So if we take a look at this truss, we see these folks are pulling on it. We want to start developing an understanding of forces, but we want to be able to characterize them between the idea of internal forces and external forces. For example, if you push on your buddy's head, that's an external force. But if you take what's inside apart and look at what the effect on the insides, that's an internal force. If you take a look at this, we have these guys. This is a truck sitting here, and we have external forces applying. They're pulling on a rope. The rope is attached to the truck, and that force that they apply is an external force applied along the axis of the rope. We can also see we've got external forces of the reactions of the ground pushing up, because the weight of the truck is pushing down. Now, we can actually kind of consider the weight of the truck as an external force, even though it's introducing internal forces. And the reason is that the mass distribution is causing forces to pull down on everything, and then we can look at section cuts that tell us how much is inside. When we talk about internal forces, we then rip it apart. Let's take a quick look at this idea. If we say, okay, if I have a rod, let's just say we have a rod, let's say it's a wrench, okay, a box wrench. And if we apply a force this way, force P, that's an external force, and it's reacted by a reaction back here, let's call that R. R equals P in this case. These are external forces. However, if we take a section cut through here and redraw this half of it, we find out that this P is reacted by this internal force. We'll call it P1. Now P1 is just P, but that is now an internal force because we have cut the member open and looked at how it's applied. If we take another little cut here and draw this little segment here, we would see that little segment has P1, this same force here, and it's reacted by another force, P2, which P2 is equal to P1. We can sum our forces in the x direction. Those equal to 0. We see P1 minus P2 equals 0, and we see that that hasn't changed. And at the other end, then we can see that this is pulling P here, equal in action, equal and opposite pairs, and this is back to our R. So we applied P, we have an equal and opposite reaction. Now on the other side of that cut, these are both, this is looking at the right side and the left side, these two pictures here. This was pulling this way, which means it's pulling the equal and opposite on the other side of that plane. That's just this face, what happens to this side of the face to the right and the other side to the left. So this is the same force, equal and opposite here. Then we sum our forces, we find out this is reacting it, flip its sign on the other side of that cut, and we see it's reacted over there. So these are external forces, these are internal forces. In terms of this truck, we see we have an external force, the force in the rope. We have what we could call an external force, the mass of this thing, we'll just call it the weight, already multiplied by gravity, and we have a couple reactions, R at the rear wheel and a reaction at the front wheel. These can be determined as external loads, and if we took a section cut through this puppy, which we haven't really done a lot yet. We've got this external load R front, this external load P rope, and now we can have various forces and moments that we haven't learned about acting on that, reacting it. These are all internal. So we get the idea of external forces versus internal forces. Got that? Key idea. We're going to be seeing this. I got a little bit ahead of us in a couple areas, but we're going to be seeing these same ideas over and over and over again. So here is that free body diagram I already sketched for you. You've got your wheel reactions. All of these can be considered external forces. And then if we start making section cuts and looking within the truck, then we'd be talking about internal forces. In fact, we could have also done the same thing with the rope. If we had, for example, cut the rope right here, we would see the rope is sitting this way. These guys are pulling there, and this is the internal force in the rope is just P, whatever force they're applying. If each guy pulls with a force of, say, 100 pounds, that would be 300 pounds of tension in the rope, and that 300 pounds is an internal force in the rope. But what it's doing to the truck, it's an external load to the truck, and then it becomes an internal load to the truck as it goes through the truck. These boys place an external load force on the rope, but as soon as you cut the rope and look at what's happening inside, it becomes an internal force. Got it? Internal versus external forces. Okay. The next idea is going back to what we do with vectors, and that's the idea of transmissibility. What this basically says is if you have a force and it has a line of action, you can actually slide that force along that line of action and don't change squat. Now, actually, that's maybe too strong of a statement. It will change the internal forces. If you have a force applied here, that means there's no force above it, right? It's only acting on what's below it. If you slide up here, now the internal loads are changed, but the conditions of equilibrium on that whole rigid body are unaffected. So we're talking about rigid bodies and how they respond to external forces. What we're saying is translating a force or sliding it along its line of action does not change the conditions of equilibrium. That's what this is saying, okay? So whether we put the force up at the upper part of the rigid body or the lower part, the equilibrium of the entire rigid body is going to be affected in exactly the same way. These are equivalent forces. This means that we can slide that force of the rope anywhere along the thing, and it's not going to change the conditions of equilibrium on the entire truck. Once again, it will change the internal forces based on where those loads are applied and what section cuts we're making and what other external forces are applicable on the part that we cut off. But it will have the same effect. So these guys pulling on the rope from one end has the same effect on the truck's equilibrium as if they had been in the back and pushed with the exact same force, as long as the line of action is unchanged. Comprende? ¿Te gusta? ¿Te piace? Nishi Juanma? That's what we're talking about. Okay. Now, vector products. We actually go into that in video 5A, which basically we're saying when we define the vector product, and I'm going to get a little more on this slide, we're defining it as PQ sine theta. So if we're taking the cross product or the vector product of P with Q, then we would take the magnitude of P, the magnitude of Q, and sine of the angle between them, and that is the magnitude of the resultant. That only tells us about the magnitude. If we want to know the direction, we're going to use the right-hand rule, take our bladed hand, poke it in the first vector direction, P, wrap our fingers toward the second direction, Q, and our thumb is pointing in the normal direction. That's the direction of the resultant, and that's how we know what direction it goes. So PQ sine theta gives us the magnitude. Right-hand rule gives us the orientation or the direction of the resultant. Like I said before, lecture 5A goes into this in detail. Okay? We also covered the rules in 5A. Okay. We also in 5A, we talked about that. Now let's take 1 second to elaborate because I realize there's one thing I left off. Remember, we're defining this cross product P cross Q, both of these are vectors, as the magnitude of P, the magnitude of Q, sine theta. What this means is, if we take the cross product of I cross with I, what this means is the magnitude, these are unit vectors, right? So the magnitude is 1 times sine of the angle between them. The sine of the angle between I and I is 0. Therefore, this is 0. That means all this stuff is 0. That's what this says. If, on the other hand, we take I cross with J, our magnitude is going to be 1 times sine of, these are 90 degrees apart. So that's going to be I with J, 90 degrees is going to be 1. If we had negative 90 degrees, we're going to get -1, and so on. And that's what all this is saying. Once again, lecture video 5A goes into this in detail. Watch that carefully. That will tell you how to do the rest of this. This is the common little IJK in a circle method that actually is kind of pansy-ish, and you're going to have trouble remembering it, but many books cover that. Or you have the Bruce Lee approach, which I described in our 5A video. This will master that, and watch what I do there with these IJs, and that will help you as well. Okay? Once again, while this is very insightful and educational to go through the process of multiplying out those components, usually the way this is solved the most efficiently is just by setting up this mathematical operation where we take this times that minus this times this minus this times quantity this times this minus this times this plus this times quantity this times this minus this times this. Once again, video 5A goes into this in detail. Check that out if that's not crystal clear. All right, let's get back to how this applies to statics then. A force vector is defined by its magnitude and direction. We already know that. However, its effect on the rigid body is affected by its point of application. Now, we already said we could slide that vector along its line of action without changing the equilibrium of the thing. But if we have it, if it's not sliding along that parallel, if we apply it in a different place, it's going to have a different effect. If you picture taking a globe and applying a force right through the center, you're going to get a translation. If you picture applying that force off to the edge, you're going to get a rotation and a translation potentially, okay? So that's what we're talking about. So what we see here is we have this rigid body and we have point O. And what we're looking at here, we have this point O, we have this force that's applied out here, and we're going to find out that the moment is defined as the cross product as the vector from whatever point we want. So let's say we want to know what, this is, point O is the center of mass. So to determine whether or not this mother rotates or just translates, we're going to need to sum up forces and moments. If this force acts through the center of mass, all we will get is a translation. If it is applied anywhere else, we will get a translation and a rotation because we're going to move that force to that point and we're going to end up getting a moment equivalent to that. We're going to find out that the moment is just if we take the point, we want to know how much rotation about the point and take the vector from that point to any point along the vector. Now, in this case, we've just picked a point on the vector. Here's the line of action of the vector. Pick any point and write what that R is. That means we're going to have a I plus something J plus something K. That is our R vector. Pick this point, pick any point on this line of action, and define what that vector is. And when we take the R crossed with the vector force, we will get the vector moment that's caused by this. That is the basic principle. I'm actually getting ahead of ourselves, of us. So let's go ahead and look through this. This is the moment of that force about point O is defined as, so what we really should say here, if we want to be more explicit, we should say the moment about O due to F is equal to R from the O to any point along vector F. Got that? That's that. The moment of F about O is this R vector, which is from that point we want to rotate about, we want to understand the rotation about, to any point along that vector F. Don't worry, it will work out. Multiplied by the vector magnitude, which means you're going to take that force's x component in the ij direction, plus that force's y component in the j direction, plus that force's z component in the k direction. That is the vector force F, and we're going to take the cross product of this crossed with this. Now, we already know that the cross product, the magnitude of that mother, is just R, magnitude of R, magnitude of F, sine of the angle between. Okay? We already know that in this case. We're going to take this, extend this line, and extend our vector line, and going from the axis of the positive R, that angle it makes in that plane with that vector toward the positive direction of that vector, that's the theta we're talking about. Magnitude R, magnitude F, sine of that theta, that gives us the magnitude of M. But if we take this cross product, we don't only know magnitude, we know everything. We know magnitude and direction. And I told you before, in industry, we're going to do this a lot. Oh, another thing we're going to find out here is this F sine theta, or this R sine theta. Actually, what that is, R sine theta, is just going to be that perpendicular distance. That gives us the perpendicular distance. Since this is perpendicular here, the perpendicular distance is R sine theta. So we're going to find out that just F times that perpendicular distance is the magnitude of that moment. This is the way we usually do it in industry. And as you develop some proficiency, most of the practical problems you're going to see in aircraft analysis, and a lot of rocket analysis too, will be simple scalar analysis like this, forces times perpendicular distance. However, when you do anything more complicated, you're going to need to understand cross products and dot products, as I keep saying. So the moment vector M is perpendicular to the plane. Okay, so that once again, the cross product is defined. So when we say, okay, we want to understand what moment does this F cause about O, we're taking our hand, we're jamming it along the axis. Once we define what R is, we jam it along the axis of R. We wrap it, our fingers in the direction of F, and the direction of our thumb tells us what the direction of that vector is. What that means is when a moment vector is pointing up, it means it's rotating like this. It's like it's spinning that thing like this. A lot of times we would show a vector that looks like this to do that, okay? All right, looks like I accidentally advanced my slide, so we'll go ahead and go with it. The magnitude is just RF sine theta, and R sine theta is just the perpendicular distance. Remember, I told you it doesn't matter what R you choose, right? Any line of action from this point to that vector, we could use this R, R1, this R, R2, this R, R3, or any other R. You'll notice while R is changing in all cases, R sine theta, actually not the vector, but the magnitude of R sine theta doesn't change, right? If you have this R sine theta, that's going to give you the same thing as this other R sine theta. These have different angle thetas, and that's going to adjust. So this quantity, R sine theta, is just that perpendicular distance d. That's all we need. If you can identify that perpendicular distance d, you can save yourself a lot of time and trouble and potential errors. So cross product, the magnitude is just RF sine of the angle between, which is simply F times the perpendicular distance. This idea is foundational, pivotal, and will hit you over and over and over again in statics, dynamics, structures 1, structures 2, and beyond. You may have noticed I actually was a ways along my educational journey when I realized that I kept learning calculus principles and trig principles over and over. Because when I first had the classes, I had calculus first in high school, and I really wasn't trying to master calculus. I was just trying to get a decent grade and get out of there. When I took Calculus 1 in college, I wasn't trying to master calculus. I was just trying to get a decent grade and get out of there. So I ended up learning a lot of the stuff that I learned in calculus in high school again. Then I took Calculus 2, which is based on Calculus 1, and I started relearning those same things that I should have learned before. And then I get to Calculus 3, I'm getting new principles, but I'm also relearning the things that I refused to learn. When I came back 12 years after I finished my master's and started a PhD, I ended up relearning a bunch of things that I never chose to learn the first time. I was only trying to put it in short-term memory. If you focus on learning this material, it will stay with you. Now, you might have to pop your book open and remember, let's see, cross product, what was the little thing again there? However, the basic principles you should be alert to. You should have mastered this so that you can pull that out as you go. You don't have to keep relearning this. If you have to relearn this principle every time you see anything based on this, you're actually going to have a lot more trouble learning the subsequent topics. But if you can learn it now, when you see it again and again and again and again, you can just focus on what's new, what's new, what's new. You're going to find the higher you go into master's and graduate work, the easier it actually gets, not the harder, because it gets more focused. But it will get harder if you don't learn anything from the lower classes. You need to learn some of those things so you can focus on what you're adding to the mix of your knowledge. Okay. Any force that has the same magnitude direction is equivalent if it also has the same line of action and therefore produces the same moment. Okay, that's kind of a trivial statement, but it's true. All right, let's look at this further. We already said that the moment of a force about a point is R cross F. And we clarified what R we're talking about and what F we're talking about. Let's look a little closer. Here's our force, okay? We can see we have a component that's parallel to and perpendicular to R. This is quite similar to what I described in 5A's video, okay? That component parallel and perpendicular. The component that is parallel doesn't cause any rotation to that element. It's only the perpendicular component. So you can look at this as saying, okay, I'm looking for the R that's perpendicular to my force, or I'm looking for the component of R that's perpendicular to my R vector, my position vector. Okay? So no matter where that vector is positioned, the parallel component won't generate a moment, and that's what we're talking about. But the perpendicular component does. I talked about this in depth on the last slide. Got it? We talked about this last slide. This is another way of seeing that in black and white. Okay. So let's say we have the moment of, so once again, if you look at this figure A, we see that the moment is just R cross F. We can choose any convenient R, but actually you'll notice that the easiest R to choose is just the shortest R going from O to the point. If that is our R, then actually that is already perpendicular. That R, when we say that R, or magnitude of R, sine of theta, theta is 90 degrees, this is just 1, therefore, that means that R sine theta is simply D. So if we choose a perpendicular distance D, we don't need to go through all this mess. We'll know the magnitude by just taking FD. That's the magnitude of the moment, right? Got that? Now that is causing what we're calling a positive moment because we're moving up and out of the page. Now if we had that F had been in the other direction, then we would have had right-hand rule, R going into F is going to give us a moment going the other direction. R and F for the upper picture, for figure A, is giving us a moment coming upwards, and R into F in the B picture is giving us a negative moment. See how that works? If we can identify what that perpendicular distance is and work with that, then everything gets easier. Okay? All right. talked about all this. Bang, bang, bang. That's what I just said. Enjoy. Next slide. Here we go. You ready? Hang on to your seats. All right. Now, Varignon's theorem. Okay. Oh my gosh, that's a fun word to say. Maybe you should name your first child that. All right. What Varignon does, he comes along and he says, okay, and this is kind of, a lot of the statements in math are so trivial that some of us are like, what? I'm having trouble remembering that because it's like saying, the sky is blue. Yeah, big deal. Woohoo. Okay. Some of these things are this way. So he comes along, he says, the moment about a given point, O, of the resultant of several concurrent forces, concurrent means they're all going the same point, right? Not they're the same direction, but concurrent meaning they all go through the same point. Any point, if they all go through it, they're concurrent vectors. Okay. Is equal to the sum of the moments of various forces about the point. So that what that means is, if we take all these forces, F1, 2, 3, 4, we add them together, all the components, add all the Fx components, I, all the Xy components, J, all the Xz components, K. And if we take the R crossed with that equivalent vector, that gives us the exact same moment. If we take R to that point, A, cross with F1, R plus R cross with F2, plus R cross with F3, plus R cross with F4. That's what this says. Seems pretty obvious, but that's what it says. Okay. Next idea. Let's break this down. Let's take a look. We got the X, Y, Z coordinates, and we have a force out there in space. Now, sometimes when we're looking at three-dimensional stuff, it can be hard to visualize. It can be useful to draw a box. So what we have is some point, and we have an X, Y, Z component of that point. And if we want to, and we have some force there. Now that we're seeing the three components, but this force is just going a single force in some direction. It has an X component, a Y component, and a J component acting the I, J, K directions respectively as shown here. Now when we want to understand the moment of this force, we can draw what our R is. Well, what is our R? It's just the distance, this R vector, is going from here to here. Now, the way this is done is actually we're going to take the point that we want, that we're starting with. That's the point we want the moment about. Our second point is over here at where any point along that force is, that current along that force line of action of the force. That means we're going from 1 to 2. That means our R that we need is going from O to, let's call this A. From O to A in this case. How do we do that? That means we're going to take the second point's values and subtract the first point's values. That means XA minus X0, which in this case is probably 0, times I, plus, or in the I direction, YA minus Y0 in the J direction, plus ZA minus ZO in the K direction. Notice we did the second node minus the first node for all these. That is our R vector. This is just a scalar, scalar, scalar in certain directions. Our force vector, if we had the force, all we need is the vector force is just some component in the X times I, or in the I direction, plus some component in the Y in the J direction, plus some vector in the component in the Z, K direction. This is our vector force. If we want another moment, we're just going to take R cross theta. So you can set up your little determinant. You can actually do it either of the methods I showed you in video 5A. You put, this is the Rx component, that's this. This is the Ry component, that's that. This is the Rk component, that's that. For Z component. We have the Fx component, the Fy component, the Fz component. That means we're going to have I, Rx, Ry, Fz minus Fy, Rz minus J, Rx, Fz minus Fx, Rz plus K, and now we're focused over here, Rx, Fy minus Fx, Ry. Bang! That is our moment. It gives us magnitude, and direction. If you want to know the actual magnitude, you just take this squared plus this squared plus this squared divided by taking the square root of that gives you that. Okay? Let's see what else we have on the slide. It's just going to repeat what I said. Bang, baby. There we are. Got it? You'll notice this first term, this tells us what moment we have about I. This tells us what moment we have about J. And this tells us what moment we have about K. Now you notice we do this, is this times this minus this times this, right? Times this plus, this guy times that minus this. I'm sorry, I was too careless. This guy times this minus this times this. And that's a minus. And then this guy times that minus this, as we said before. But the second term is minus, but you'll notice instead of a minus here, they just swap these terms. No problem. We can deal with that. Okay. Ready? Okay. Now you notice this is kind of almost the same thing, but now our first point is not a 0 anymore. However, what I described on the last slide gives you everything you need. So we have some point out here, B. We have some point out here, O, A. And we now want to know the moment of F about B. Now, if we wanted the moment of F about O, we would have needed this vector. But if we just want the moment about B, we'll just need this vector. How do we get that vector? It's just the X, Y, and Z components of node 2, where we're calling node A, minus the X, Y, Z components of node B. Got it? Woohoo! Starting to sound familiar, starting to sound a little redundant. This hopefully is starting to sink in, so this becomes second nature. Okay? Blah, blah. Done. Got it? You can study this at your leisure. Actually, if you don't get any of this stuff that I'm telling you, or who your other teacher is that's telling you, rewatch the video. Ask your professor, study the book. These elementary texts, Beer and Johnson's Vector Mechanics, Merriam and Craig's, Hibbler's, and others, all deal with these kind of ideas quite well. And they have example problems. Those example problems, some of them have, those all have detailed solutions. And then in each section, there are problems that you can practice and look in the back of the book, and a roughly 30% to half of them will have answers in the back of the book. You can check your understanding, make sure you understand these concepts. If we have a two-dimensional structure, it gets a little simpler. In this particular case, we have this force. Now, there's a couple ways we can solve it. Remember, we can just solve it as FD. If this is the line of action of the force here, and we want the moment about point O, all we have to do is extend this line and figure out what the perpendicular distance is. We can just multiply magnitude of F times that distance, D, is equal to the magnitude of our moment. However, sometimes it's hard to figure out what this perpendicular distance is, and it's easier just to say, okay, R is simply x2 minus x1 I, y2 minus y1 j, z2 minus z1k crossed with whatever the fxi, fyj, fzk is of this vector. And it gets simpler for in 2D, we only have moment about z. It gets a little bit mas, facile, a little easier, okay? Here's a little example problem. This is saying, okay, we're looking for what is the rotation about point O. We have this 100-pound force. We can do two ways. We can define Rx and Ry and cross that with our vector force, which is minus 100J, right? Minus 100J. It's 100-pound magnitude in the minus J. Take that cross product, bang, gives us everything we need. Another way is to calculate what is the perpendicular distance. It's just 24 cosine, in this case, 24 cosine 60 is the perpendicular distance. That's the perpendicular distance from this point. So what you see is we're extending the line of action here, and we're finding the perpendicular distance from the point parallel to that. That's D. If we use that, calculate that value, which is just 24, in this case, cosine 60, that value times this will give us your moment. That's another way of doing this, okay? And this is how that works. This is using the perpendicular distance approach. Normally we'd call this negative because when you take R into J, you can see it's going into the page rather than out of the page. Right-hand rule, out of the page would be positive. Okay. This is looking at that further, another way of doing it, blah, blah, blah. Why must the direct, okay. Oh, this one is asking what horizontal force can we place at point A, which will give us the same moment. Well, in this case, we're just solving backwards. We're just taking this perpendicular distance times that force and equating that to the moment we had, and we calculate what that force needs to be. Not a big deal. Which force, here's another conceptual question, which of these forces, there's 4 forces shown here, red forces, which one will require the smallest force to have the same moment? Well, obviously, it's the one that's perpendicular to that R. If it's perpendicular to the R, then that sine theta is not reducing that projection. You're getting the full force acting on the thing. So perpendicular. And you kind of know this if you ever try to take your lugs off on your tire. You don't pull on the wrench. That's not going to turn that wrench. You need the further out you get. And if you can't break it free with a force here on your little pansy short wrench, you go get a big pipe, stick it on the end so you can have your little sister sit on the end of it, and that causes a much larger moment. Okay, that's what we're talking about here. Bang. This, okay, we don't need to go through these details. You can study these on your own. These are in your Beer and Johnson text. Okay, this is a little trickier one. Let's take a look at this for a minute. Here's another typical kind of problem, and we have this little plate. Now, this causes us a lot of times to pucker up and go, I can't do this, but you can. When we don't know what to do, we sit down and say, wait a minute, I studied this stuff, I know this stuff. What do I know? What do they want? And then you systematically walk through the things you know. So let's take a look. We got a rectangular plate. Great. It's supported by brackets A and B. Fine. By the wire CD. Fine. Looks like we get a lot of information. We're probably not even going to use all that. Wire CD. That's this wire here. Great. Okay, got it. Knowing that the tension, if that tension in the wire is 200 newtons, determine the moment about point A of the force exerted by the wire at C. Okay, so what this means is if we take a look at this, we're going to use this point A, and we want to know how much rotation is caused by this wire. Well, if this wire is in tension, if we draw a free body diagram, what we would do is cut this off, and we would replace it by a force. That means if we remove this wire, we're gonna replace it with its tension, which means, let me use this. If we draw this out, here's our thing. That's our shelf. We're talking about a moment at A, and at this point, we cut that wire off and we replace it with its force, and we call it T. We know what the magnitude of that tension is. All we want to know is what is the moment of this force acting about point A. What that means is we're going to say, okay, we need the moment about here. So we're going to get the position vector R from the point we want the moment about to any point along the line of action of A. That means we can either use this line or this line. I'm going to choose this lower line. I think this is a better choice. Okay, this is our R. We could say it's R from A to C. So R from A to C. That means we're going to take point C minus point A. So what this means is we're going to have XC minus XAI plus YC minus YAJ plus ZC minus ZAK. That is our vector. So if we look at this, we say, okay, let's take a look at a coordinate system. Let's just choose our coordinate system Actually, let's just do this. Let's make the coordinate system right here. We'll say this is x, this is y, and right-hand rule x going into y, this is z. Okay, if that's true, then we see moving in this point C, point A is now at 0, 0, 0. Point C, according to that coordinate system, is at 300, which is 0.3 meters, right? 0.3 in the x, it is 0 in the y, and it is, excuse me, yeah, 0 in the y. Oh, C, 0, we said 0, 0. Point C in the y direction, what's our y direction? Oh, excuse me, it's not 0. It's at minus is this dimension. It's, since that's positive y, it's at minus 0.08, 0.08. It's minus 0.08 because we're not on the positive, we're in the negative direction from here to here, okay? And then our z is actually 0. Okay, so our vector then is going to be 0.3 minus 0, I, plus minus 0.08 minus 0, j, plus 0 minus 0, k. Got that? That means our r is 0.3i minus 0.08 j, and we can say plus 0k, or we can just leave that off. Okay, what is our force vector? Now, the beauty of this is, now it looks like we got two unknowns, magnitude and direction, but we know the direction of the force. So actually, the force is acting, we already know the magnitude of the force, t, right? So all we need to do is let's get a vector along this force t. We're going to need a unit vector. So what we need to do is choose any two components. So we're going to go from, now this force is acting from point A. Let me go ahead and erase what we have. Erase all this stuff. Okay, when we look at this, we said that this, oh, I need, hold on. We said, let me get this back, my pen. Okay. We actually identified this is our x. We said this was our y, and this is our z. Now I'm just doing this on the fly. When the book solves this problem, they may choose a different coordinate system. No big deal. Now we're dealing with this guy here, and we're trying to find out what we're going to first need the unit vector. We already know the magnitude, so let's just choose two convenient points. We can see that this line of action of the force, let's just call it, okay, let me do this. The vector force t is just the magnitude of t times the unit vector of that force. This is the unit vector of the force. What is the unit vector? All we need to do is find out any convenient distance along that. And for us, we can find these two endpoints. That's the easiest way to do this. So actually the unit vector of t is actually goes, now we're going to go in the positive direction, which means we're going from C to D. All right? So if we want to know what the vector is along there, the non-unit vector, we can just say CD is a vector. And it is the distance between the endpoints. That means it's point D minus point C. So let's write out point D. Point D and point C. Point D is here at 0x, 0, comma, and the y is at 0.24. No, that's not the y. Yeah, 0.24, comma, and the z is also 0.24, it looks like. So there's the y, and here's the z, 0.24. Point C is out here, and it is, we already said what it was at. It's plus 0.3, 0.3 in the x. In the y, C is at minus 0.08. And in the z, it is at 0. Okay, so CD is going to be x of C minus x I'm sorry, we're going from C to D. So this is actually xd minus xc I plus yd minus yc j plus zd minus zc k. Got that? So that means it's actually going to be 0 minus 0.3, so it's minus 0.3 I. We're going to have d minus c, which is 0.24 minus 0.24 minus, which is actually a plus, 0.08 j, it's a plus, and then we've got 0.24 minus 0 k. Got that? That gives us our CD. Now, if we take the magnitude of CD, the magnitude of CD is just that squared plus that squared plus that squared. Right? Square root of all that, that's a magnitude. So if we take this vector CD that we just calculated, divide by its length, CD, that we just calculated, that squared plus this squared, square root of all that, that is going to give us the unit vector along CD. The force T is now going to be the unit, is going to be the magnitude of T, which we said was what, 200 kilonewtons or 200 newtons, times that unit vector along CD. So when we solve these kind of problems, the first step is to find what is the any position, convenient position vector along the vector going in the positive direction along the force. And we get the endpoints of that. We turn the endpoints into a vector, position vector CD. We then divide the position vector by its own length, and that gives us the unit vector in the direction of the force. The force magnitude is just that unit vector times the scalar force magnitude. And then we're ready. We've calculated the R already in our previous step, and we take R cross F with our second step, and now we're ready to solve this. Now, so that shows you up ahead of the game conceptually how we do all this. Now we're going to walk through it using the book solution. This is what we're after. And the way the book calls that is C. This is the position vector of C relative to A. This is one way of writing it. I like to say that this is RAC rather than C coming from A. This nomenclature shown here is C coming from A. I like to call it in the positive direction, going from the first endpoint to the second. We're always going to take the second minus the first. So that would be, I would call that RAC, and I would call that FCD, both acting in the positive direction. Okay? This is how they're going to solve it. Bang, bang, pop. Once again, look, they used a different X, Y, and Z. No problem. We can deal with that too. That gives a little different numbers. It's actually useful that I use a different nomenclature, so you can see that if you do it a different way, you get exactly the same number. Assuming that I didn't make any bumbling moves under pressure of doing this so fast. Okay? And that gives us our moment. See how that is? If you want to know what the magnitude of moment is, you just take the square root, the sum of the squares, right? This 7.68 minus 7.68 squared plus 28.8 squared plus 28.8 squared. Take the square root of all that mamba jamba. That gives you the magnitude of the moment about that point. But this vector tells you everything you need to know about that moment. Okay? Great. We talked about this in lecture 5B. Study that. This was just saying the dot product is defined as P dot Q is defined as the magnitude of P times the magnitude of Q times the cosine of the angle between them. Watch that video. That tells you how to unravel all this stuff. We looked at this in that video also. I will just refer you to video B. We covered this in 5B. If you refer to that video B, this is talking about the unit vector. We probably should have covered this before the last couple slides, but you actually watched 5A and 5B before this lecture, so you should have been armed and ready. Okay, we also talk about triples, mixed triple product. You're going to start seeing some applications of that maybe today and as we go forward. Once again, watch that 5B video to understand this. All right, so when we want to know the moment of a force about an axis, what we're going to do first is take the position vector from the point we want the moment about to the force. We're going to cross that with the vector force. That's a cross product, and that gives us the moment about the point. If we want to know what that moment, what component of that moment acts about a certain axis, all we need to do is take the dot product of that resultant moment with that, the line of action, the vector defining the line of action, or the unit vector defining the line of action of that line that we want to see the projection on. Now, if we use any old vector, we're going to end up getting some scale factor against that projection. So we need a unit vector when we do this dot product, so we don't change it, we just see the projection. So because the moment is defined with this cross product and the projection is defined with a dot product, this uses the mixed triple product, goes straight from the force to the projection using that RF and the unit vector in the direction of the line of action. That's what all this says. You can study that at your leisure. Look in your book for examples. Okay. Once again, so this is another method. Let's say we have some moment and we want to know what the moment is about a given axis, right? So we know if the force is parallel to that line of action, it's not going to cause any moment. But if it has any components that are not parallel, then it will cause a moment about the axis. It might be a moment in an I, J, K, or all three of them. All we need to do here is, once again, pick any point along the line of action. In this case, it looks like we chose B. Pick any point along the line of action of the force. It looks like we chose point A. Find the endpoints of the position vector. We're going to be going from B to A. I'd call that BA. I'm not giving you a BA. I'm talking about a BA. Our position vector is BA. A lot of times instead of that, we'll just say BA that. That's showing it's a vector, a position vector from B to A. We then are going to need to know what this vector of the force is, the I, J, K, and that. And then we can just take the product, the cross product of that position vector BA cross with F. That is going to give us the moment of that force about point B. But we didn't want the moment of the force about B. We wanted the projection of that moment on that line of action. So now we're going to take the dot product of that moment which we just calculated, MB equals R, which is actually BA, cross with F, right? And so that's the moment. And now we're going to take the dot product of the axis we want dotted with this moment will give us the projection, the moment on that line of action, which we could call BC. That's the projection onto that axis. This is a mixed triple product because we're taking lambda dot R cross F. Comprende? Let's see what we say on the slide to support these ideas. Bang. Okay? Here's a little example. Let's see. We have a cube. We got a force acting. Determine the moment of that force about point A. So we're going to need a position vector. Our position vector, we can just choose AF would be fine. That looks like it's, if our cube is a AAA, then that's going to be AX. Oh, let's do that real quick. Let's just say this is X, this is Y, and this is Z. Then if we want the moment about A, then we can use either this vector, AF, or we can use this vector, AC. Let's use AF. AF is going to be, moving from A to B, we're moving plus 1, F minus A is moving in the plus A direction. So we got AI, and we have minus AJ. That is AF. And our force, then, we can say, well, what is FC? FC looks like it's going to be 0I, because it's not moving that way anymore at all. It's moving plus AJ, and it's moving in the positive direction, AK. Okay? Now, all we have to do, now that is the FC. We're going to need the unit vector along this direction, which means we calculate the magnitude of FC, which is this squared plus this squared plus this squared, the square root of all that. And then if that unit vector along FC is going to be FFC divided by the magnitude of FC. What that means is you take this magnitude and divide each of these terms by it. And that tells you what that unit vector is. You then take the cross product of that unit vector of that first vector, what was it, AF? Our moment about A of force P is going to be equal to AF crossed with magnitude of P times a unit vector FC, right? That's going to be your moment about point A. And we could have used the other point, the other position vector, and got the exact same answer. Okay? Oh, here you go. This does it all for you. Bang, bang, pop. Okay? Here's another problem. Bang, bang, pop. Another problem. Bang, bang, pop. Study those. Look in your textbook for more examples with answers to check your work, so that you master these principles and you no longer have to think about them to nail them. If you get a good calculator like a TI, Inspire, or something like that, it will do a lot of these operations for you, but you need to understand how they work. Oh, you also need to check and make sure your professor allows you to do that. If you haven't subscribed to my channel, if you found this useful, this is a good time to subscribe so you stay connected both while you're in your undergraduate work, as you go on to some of your master's work and later in industry. You will likely find, if you're in structures, you will likely find some of my content useful throughout your career, and some of my handbooks that are for later classes. So enjoy. I hope you find this useful. If you do, so I'm actually not teaching statics this semester, but if you find this useful, like the video or email me, and I will try and get more of my statics videos uploaded as, or statics lectures uploaded as videos. Hope you find it useful. Go out there and be great. Hasta luego.